Okay, calculus, last section, 15.4. It's Green's theorem, and it's primarily about pathways around a region when you traverse the region one time. This theorem states the value of a double integral over what's called a simply connected plane region R is determined by the value of the line integral around the boundary of R. A curve C given by the vector value function x of ti plus y of tj, where t is between a and b, is simple when it does not cross itself. That is, r of c is not equal to r of d for all c and d in the open interval a, b. So basically, it's not like a figure eight. You can make a zero around an area. You can kind of make like a D, but a figure eight where it crosses itself is not allowed. A connected plane region R is simply connected when every simple closed curve in R encloses only points that are in R. Informally, a simply connected region cannot consist of separate parts and wholes. So like these two are not simply connected. This one is not simply connected because they're two separate regions not touching. This one's not simply connected because there are extra holes inside, but this one up here is simply connected. So Green's theorem says, let R be simply connected region with a piecewise smooth boundary C oriented counterclockwise. That is, C is transverse to 1, so the region R always lies to the left. If M and N have continuous first partial derivatives in an open region containing R, then the integral over C of M dx plus N dy is the double integral over R of dN dx minus dM dy dA. So it's an area. So let's just talk about how we use this. Use Green theorem to evaluate the line integral where C is the path from 0, 0 to 1, 1 along the graph of y equals x cubed, and from 1, 1 to 0, 0 along the graph y equals x. So it's traveling up and around and then back down. So I need both partials. I need the second one in terms of x. So dN dx is 3x squared plus 3y squared. dM dy is just 3y squared. Now it converts to a double integral here. I have to subtract these two. So dN dx minus dM dy, the 3y squareds will cancel, so it should just be 3x squared. Now I'm going to dy dx, the area first. Y varies based on x. It starts by going along x cubed and then goes back along x. If we do y first, then x is going to vary just from 0 to 1. Okay, so what's the integral of 3x squared with respect to y? It's 3x squared y evaluated from x cubed to x. So that'll be 3x cubed minus 3x to the fifth. I need to take this integral from 0 to 1 dx. The integral of 3x cubed is 3/4 x to the 4th minus 3/6 x to the 6th evaluated from 0 to 1. So that's 3/4 minus 1/2, which is 1/4. That's the value of the area using Green's theorem. So this could have been slightly more complicated. This one, not so bad. Now, you can also use the theorem to evaluate double integrals as line integrals. We just converted a line integral to a double integral, but we also can go backwards. One useful application occurs when the difference between these two is 1. The area is then 1/2 x minus y. Now, let's see how this works. If R is a plane region bounded by a piecewise smooth simple closed curve C oriented counterclockwise, the area of R is given by 1/2 the integral of x dy minus y dx. Because among the many choices satisfying M and N satisfying this stated condition, the choice of M equals negative y over 2 and N equals x over 2 produces the following line integral for the area of the region R. So this is the simplest one. So how can we use this? Use the line integral to find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Okay, so if you let 0 to 2 pi for t, x is then a cosine t, y is b sine t, dx is now negative a sine t, dy is b cosine t. Now it says the area is 1/2 integral over c of x dy minus y dx. Well, that's going to be 1/2 the area, or the integral from 0 to 2 pi of x dy. So that's ab cosine squared t minus y dx, which will be negative ab sine squared t, dt. Minus negative becomes positive, so now this is 1/2 the integral from 0 to 2 pi of ab cosine squared t plus ab sine squared t dt. And we know sine squared plus cosine squared is 1. This is just the integral from 1/2 the integral from 0 to 2 pi of ab, which is abt evaluated from 0 to 2 pi, which is just 1/2 times ab times 2 pi. 2 and 1/2 cancel, so it's ab pi, the area of the ellipse. Now, this is the last math problem. The rest of the notes is just some interesting facts that allow you to draw further conclusions with Green's theorem. It's just really just an exposure to its base use. And that's all for the notes for 15.4 and the rest of the class. And I hope you enjoyed Cal 3.